We did an example, right? 4x plus 12 equals 0, right? That's equivalent to saying x plus 3 is equal to 0. Basically, anytime you do an operation, the same operation on the left-hand side as you do on the right-hand side, you get an equivalent equation, right? Okay. And what does it mean to be equivalent? It means that you have the same solution set, right? So solving this equation, which is a little bit more challenging, is the same as solving this equation, which has smaller numbers in it, right? Fair enough. Yeah. And that's the same as solving this equation, right? But this equation's already solved. X equals -3 is the only solution, right? Yeah. So that's the solution set for all three of these equations. Okay. All right. So that's just bringing us up to speed here. Right now we're back on section 1.2. Okay. So where is my pen? There it goes. All right. So now that we've done that, let's try this. So let's practice solving equations. So what I said earlier was, as long as you do the same operation on the left-hand side as you do on the right-hand side, right, you'll get an equivalent equation. And that's true. Yeah. But I mean, what operation should you do, right? Yeah. So this is going to be sort of like guidelines for what you might do here. We're going to do a little bit of trial and error on it to see why sometimes some things are better than other things. Okay. So let's consider 2x plus 3 equals 17. Okay. So that's an equation, right? A linear equation, right? It's not in the form as above, but if I were to subtract 17 on both sides of the equation, then it would be in that form, right? Okay. Now, here's what we're going to do. We can use arithmetic, right, to simplify this equation to come up with an equivalent equation, right? So, for instance, we could capitalize that. We could start off by dividing both sides of the equation by 2 if we wanted to. Okay, we could do that, right? We could divide by 2 on both sides of the equation. Okay, so what would that look like if I did that? Right, so I have a 2x plus 3, right? I have a 17, right? And dividing by 2, and I don't know if everybody knows this, right? So stop me if you don't. But dividing by 2 is the same thing as multiplying by 1/2. Everybody okay with that? Yeah. Most of the time I'll express division as like, multiplying by fractions, right? For reasons for simplification purposes. Okay. So here I go. I divided everything by 2 by multiplying by 1/2. Okay. Yeah. All right. So good. That's what that looks like right now. So I've multiplied by 1/2 on both sides of the equation, right? Okay. Now, the good thing about multiplying by 1/2 is, well, when I do 1/2 times 2, they're going to cancel off, right? So 1/2 times 2x is just the same thing as x, right? The 1/2 and the 2 will cancel off when I multiply them together, right? Cancel to 1, I should say. Okay. But we have to distribute, right? So this 1/2 also gets multiplied by this 3 over here. So this would be x plus 3/2, right? On the right-hand side, I just get 17/2, right? So like I said, we could divide by 2 on both sides of the equation, right? But I would argue that maybe this equation is not simpler than the equation that we started with, right? Yeah, 2x plus 3 equals 17 has nice whole number values, right? Yeah, and then over here I've now introduced fractions, which nobody likes, right? Yeah, so maybe dividing by 2 is not the best way to go about it yet, right? Okay. Yeah. Ultimately, I want to say what x is equal to, what x is satisfy that equation, right? So I want to get x equals something. So I could, from this point, subtract 3/2, right, on both sides of the equation, right? Let me do it a little bit neater, since we're learning how to solve this now. Yeah, so no shortcuts. So x plus 3/2, if I subtract 3/2, that'll get rid of that, right? 17/2, if I subtract 3/2, that'll get rid of that. So this 3/2 cancels off with this, and now I just have x on the left-hand side. On the right-hand side, I have 17/2 minus 3/2. Do we remember how to subtract fractions, right? Yeah, add and subtract fractions, right? As long as they have a common denominator, right? Then we can put it as a single fraction, right? So there's your common denominator of 2 between those two fractions. And then now we just subtract the numerators, right? This is like saying you have 17/2, and now I'm taking away 3 of those halves, right? So then I'm going to have 14 of those halves left over, right? Yeah, fair enough. And then 14/2 is just 7, okay? So yeah, I solved it, okay? I don't think that was the easiest way to solve it though. Okay, so here's what I'm going to do instead. Okay, I'm going to solve this in an alternate way, right? So instead, there's just too much stuff on this desk. Somebody has to reorganize this room. I think I'm going to come in here on a weekend and just reorganize everything. So if you find the desks moved around like next Tuesday when you come in, I did it. So, all right. So instead, why don't we start off, right? So solving the same equation again, 2x plus 3 equals 17 by subtracting, oops, so, no, get, oh, okay, there we go. By subtracting 3 from both sides. Okay? So if I did that, right? Well, we had 2x plus 3 equals 17, right? And then now I'm going to start off by subtracting 3 on both sides. Okay? If I do that, well, this 3 cancels off with this one. They subtract 0. I have 2x left over on the left-hand side. Over here, 17 minus 3 is clearly 14, right? And then now I can divide by 2 on both sides, right? So I'll have 1/2 times 2x. It's the same thing as 1/2 times 14, okay? And then 1/2 times 2x, 1/2 times 2 cancels to 1. So I just have x left over. 1/2 times 14 is 7, right? So x equals 7. And that just looks a lot nicer, right? Okay, fair enough. Yeah, it worked both ways. I'll point that out. Yeah, it doesn't matter. Like you get the same answer at the end there, right? Yeah, you had to do the same operations even. It's just that you did them sort of in a different order, right? Yeah. But if you're looking for simplicity, right? Oftentimes it's easier to do your subtractions first before your divisions, right? Yeah. So I just wanted to kind of point that out there. Okay. Yeah. And it really is just sort of a, you got to try it and learn, right? Trial and error, we'll say. Okay. Let's try this one. Okay. Let's call this an active engagement assignment. Okay. That's our first active engagement assignment. And it should be easy. Should be pretty easy. But if you have any trouble with it, definitely raise your hand and I'll come around and check it out, right? So we're gonna kind of show our work for this one, right? Get out a blank sheet of paper, right? Yeah, even if you don't think you'll use the whole thing, please use a whole sheet of paper anyway. Yeah. Um, so let's see here. So this is our active engagement assignment. All right. Solve and check. 4x plus 5 equals 29. Now, what do I mean by check? I mean, once you find the x value that works, plug it back into the equation and make sure that you got the right answer, right? Because I want everybody to get like 100% on this thing. Okay. Yeah. Okay. So I'll give you guys, say, 5 minutes on this. I'll walk around the room. Guess I should have reminded you guys to put your names on. Sorry about that. Everybody did put their name on it, right? All right. So, and what I was saying about the active engagement assignments before is that this is like basically like a quiz grade, but I don't like calling them quizzes because it's more like, practice, right? And like I will come around and help you if you're struggling, that kind of thing. And of course, this problem was like really easy. The problems do get more challenging as we go through the semester. So like, you may require a little bit of extra help. But ultimately, I just want everybody to get 100 on it. Okay. Yeah. All right. So let me get back to this. Where to put it? How about right there? All right. So now let's solve this together. So we have 4x plus 5 is equal to 29, right? And like I was saying before in my suggestions above, it's usually better to do subtraction before division, right? Usually, not always the case. So I'll subtract 5 on both sides, right? So I have 4x plus 5 here. I'll subtract 5. I have a 29 here. I'll subtract 5, right? And from that, I'll get that 4x is equal to 24, right? At this point, I can divide by 4 on both sides to get x by itself, right? So I'm just going to do 1/4 times 4x is equal to 1/4 times 24. So I get x is equal to 6, right? That's all I was really expecting for you in terms of solving. You don't have to show me your work for checking it, right? Yeah, but if you wanted to, here's what you would do, right? I'm going to plug it back into this. So I get 4 times 6 plus 5 equals 29 when I plug x equals 6 back into there, right? But 4 times 6 is, of course, 24, right? 24 plus 5 is 29. So there we go. All right, we get a true statement. So then it must have been a solution. Okay. All right. Any questions on that at all? Okay. So solving linear equations, pretty easy. What more can I say about this? Let's see. Oh, let's have some more complicated linear equations. Things where there are multiple x's running around, right? So how about we try simplifying an algebraic expression, okay? Simplify an algebraic expression, okay? So I'm going to have a little reminder over here, right? So I'll say note, right? Remember that equations have equal signs. That's why they're called equations, right? But expressions do not have equal signs. Yeah. Okay. Expressions are just a bunch of quantities added together, multiplied together, and whatever, right? Yeah. Okay. So equations have equal signs, while expressions do not. You can solve an equation, right? Because you're claiming that one quantity is equal to another quantity, and you're trying to find out for which x values that's true, right? Yeah, so you can solve an equation. You can't solve an expression, okay? Yeah, expression's not making any kind of claim at all. So how can you say that that expression is true or false, right? Yeah, so there is no solving an expression. There is simplifying an expression, though. Yeah, and finding equivalent ways of writing an expression, okay? Right, so I'll say this. You can solve equations, but you cannot solve expressions. Okay. All right. So now that we have that, right, let's talk about how to simplify an expression. To simplify an expression, you want to rewrite the expression in an equivalent form. Equivalent form. Right? And so for example, right? So just for example here. Let's say we had 2x plus 3, right, equals 17, right? So that's an equation, right? Right? Whereas 2x plus 3, that's an expression. Okay, fair enough. So that's the difference between an equation and an expression. This is making a claim. This thing is equal to this thing, right? And for what x values is that true? That's called solving it, right? This is just 2x plus 3. There's nothing to solve there, right? Yeah. You can plug in different x values if you want. You just get different numbers, right? Okay. So let's do an example of simplifying an expression then. Simplify 3 times x minus 7 minus 5x minus 11 and solve 3 times x minus 7 minus 5x minus 11 equals 14, right? So I want to simplify this expression, and I want to solve this equation. Yeah? Fair enough. Any questions on what we're doing here? Right, so 2 tasks here. All right, let's start with the first task, right? So we're going to start with simplifying. Okay, so I have 3 times x minus 7 minus 5x minus 11, right? No right-hand side, right? Because there's no equal sign here. I'm just simplifying an expression, right? Fair enough. Okay. What am I going to do? I'm going to write it as an equivalent expression, right? So this thing that I just wrote over here, right? Now I'm going to introduce an equal sign, okay? And then what's going to go on the next part of this equal sign is something that's equivalent to the thing that I have up here, okay? So I'm going to start off by distributing my 3 here, right? And distributing my minus sign here. Okay, fair enough. Multiplication distributes over addition and subtraction. Okay, so here I have, this will just be 3x minus 21, right? Distribute the minus sign there, get minus 5x plus 11. Okay, so that is equivalent to what we started with. Okay, any questions on that? Okay, all right. Now comes the part where we combine like terms. Okay, so like terms. What are like terms? Well, this has an x in it, and this also has an x to it. So that's going to be like terms. This is just a constant, right? This minus 21. And this is also just a constant. So those are like terms. Okay. So how do we combine like terms? Well, combining the constants is easy enough, right? We have minus 21. We're adding 11 to it, right? So what is negative 21 plus 11? We can do it in a calculator, of course, right? But it's negative 10, right? So combining those together, we get negative 10, right? So that's easy enough when we just have numbers, okay? But what about when we have x's there? Well, think of x as an object. Maybe they're apples or something. So here I have 3 apples, right? Right? And if somebody's taking away 5 apples, maybe it doesn't work really well with apples because we won't get negative apples. It doesn't make any sense, right? Let's talk about money. Here I have $3, right? And now I'm subtracting $5, right? Yeah. So then I'm going to wind up with negative $2 from that, right? So negative $2, right? So I always think of x as an object. I have 3 copies of x here. If I take away 5 copies of x, then I must have negative 2 copies of x left over. I owe you 2 copies of x, right? Okay. And that's how we combine things that have the variables in there, okay? We'll do the same thing when we have polynomials like x squared and x cubed and so on and so forth, right? Okay. But now I'm done, right? I've simplified this expression as much as possible, right? I've combined all the like terms, yeah? So then that's it for simplifying, okay? Any questions on it at all? Does anybody see where I left my coffee? Outside of the monitor. Thank you. Need this security blanket. So, now, now that we've simplified that expression, let's go to the other part of the problem where we're going to solve this equation, right? So we're going to solve 3 times x minus 7 minus 5x minus 11 equals 14. And we're going to sort of compare and contrast, see how things differ from the 2 different things that we're doing in this problem, right? So we've already simplified the left-hand side. We know that 3 times x minus 7 minus 5x minus 11 is the same thing as negative 2x minus 10. Exactly the same thing, right? So then I can just replace, let's see, let's use my purple marker here. I'm going to replace this with this, right? This is the same thing, right? So since I've already simplified that, I now know the left-hand side is the same thing as negative 2x minus 10. The right-hand side is still 14, right? Haven't done anything to the right-hand side yet, right? Is everybody okay with that, by the way? Yeah, what I've done there. Replace something with what it's equal to. Yeah, that is a key feature of algebra, something we do all the time in algebra. Replace a quantity with something that's simpler, right? That's equivalent to it. Okay, so we're going to do that in pretty much every problem. Yeah. All right, but now that I have that, right? Now I can solve this easier equation, right? So I need to get x by itself. What's the first thing we're going to do? Yeah, we're going to add 10 to both sides of the equation, right? So negative 2x minus 10 plus 10 is equal to 14 plus 10, right? So this will cancel with that, and I have negative 2x is equal to 24, right? And then now I need to divide by negative 2, which is the same thing as multiplying by negative 1/2, right? Yeah, so this is negative 1/2 times negative 2x here is going to be equal to negative 1/2 times 24, right? All right, the negative 1/2 and the negative 2 will cancel off, right? Cancel to 1. So I have x is equal to, well, negative 1/2 times 24 is just negative 12. Okay. So there we have it, right? And look how I showed my work in this, right? So when I was simplifying the expression, I just wrote the expression on one line. On the next line, I wrote something that's equivalent to it. On the next line, I wrote something that's equivalent to that, right? Always using equal signs. So this thing is equal to this thing, which is equal to this thing. Okay, right? Now that differs from the way that I showed my work for solving an equation, right? Each line of this is its own equation, so I don't have another equal sign out here, right? Yeah, yeah, that wouldn't be proper notation anyway to do that, right? Right? So this equation is equivalent to this equation, which is equivalent to this equation, and so on. They all have the same solution set, right? But it's understood that this equation is equivalent to this one if I write it directly underneath it like that. Okay, fair enough. And that's because we don't want to clutter up everything with a bunch of equal signs. Yeah. Okay. Okay. So any questions on that? All right. So let's see. Let's start talking about linear equations that look a little bit harder. Okay. Yeah. Always with the making it slightly harder than it was before, right? Yeah. Yeah. So let's do linear equations still, but this time with fractions. Okay. All right. All right. So here we're going to solve and check x minus 3 over 4 is equal to 5 over 14 minus x plus 5 over 7. Okay. All right. All right. So how do we solve this one? Well, we all hate fractions, right? Even me. So let's get rid of the fractions, right? Yeah. So what we do to get rid of fractions is we do something called multiplying by the least common multiple of the denominators, okay, which we have a shorthand name for, also known as the least common denominator. Common denominator on both sides of the equation, right? And I forgot I was supposed to be working on my handwriting here. On both sides of the equation. Okay. So our goal here is to cancel off all fractions so that we're just left with whole numbers, basically, right? Okay. All right. So I have to talk about how to find this least common denominator, right? Well, here's how I like to start off, right? I like to factor all of my denominators as much as possible. Okay. So 4, for example, is 2 squared, right? Yeah. I'm factoring everything into its prime factors, right? So 4 is just 2 squared, right? 14, that's just 2 to the first power times 7 to the first power, right? 7, well, that's already factored. It's just 7 to the first power. It's a prime number, right? Okay. All right. So I see that we have these common factors, 2 and 7, right? Fair enough. The least common denominator, right, which I'm going to abbreviate LCD for least common denominator, right, will be you have these common factors in there, right? So you have your 2 and your 7 in there, right? And you use the smallest exponent on each factor, right? So here, the smallest exponent on 2 is 1. Here, the smallest exponent on 7 is 1. So 2 to the first power, 7 to the first power, and that's 14. Okay. Fair enough. So that's your least common denominator there. Yeah, I can express all of these fractions, right, over 14 if I wanted to, right? Fair enough. Okay. I said that wrong. Sorry. I said the smallest exponent, but I meant the largest exponent. My bad. So this is 28. Oops. Yeah. So the least common denominator will be the product of all the common factors raised to their highest powers, right? So 2 squared, right? 7 to the first power. Okay. Okay. So now it says I'm supposed to multiply this on both sides of the equation. Let's see what that's going to look like. Okay. So I'm going to rewrite my equation over here. X minus 3 over 4, right? Equals 5 over 14 minus X plus 5 over 7. Okay. And then I'm going to multiply both sides by 28. So I'm going to have 28 times X minus 3 over 4. I'm going to have 28 times 5 over 14 minus X plus 5 over 7. Okay. Okay. And then now we got to simplify this, right? So here, 28, we're multiplying by 28. I'm dividing by 4, right? So I can go ahead and simplify that. 28 divided by 4 is just 7, right? So then this is the same thing as just multiplying X minus 3 by 7. And I'm going to pause there. Did I lose anybody in that step? Yeah. And doing that. Is everybody okay with that? Okay. All right, good. Now over here, I have to multiply by 28 over here, and I got to multiply by 28 over here. All right, so this is the same thing as 28 times 5 over 14 minus 28 times X plus 5 over 7. Okay. All right. So the left-hand side still 7 times X minus 3, and we kind of had to drag that around throughout the entire problem like dead weight, right? Yeah. Yes, it's absolutely necessary. Yeah, don't lose it. Okay. Now, over here, 28 divided by 14 is just 2. So I have 2 times 5, basically, which is 10. Okay. Everybody okay with that? Okay. And then now I'm subtracting something. 28 divided by 7 is 4, and I'm multiplying that by x plus 5. Okay. Parentheses are absolutely necessary there. Yeah. The entire numerator is getting multiplied by 4. Okay. All right. I'm going to go ahead and distribute this 7. I'm going to go ahead and distribute this minus 4. So I get 7x minus 21 equals 10 minus 4x minus 20. Don't forget to distribute the minus sign also, right? All right. Let me go ahead and combine like terms on both sides here. So 7x minus 21 is going to be equal to negative 4x minus 10. Okay. Okay. Now I need to get all of my x's on the left-hand side and all of my constants on the right-hand side, right? Okay. So that way I can solve for x. So I'm going to add 4x to both sides of the equation. So I have 7x minus 21 plus 4x is equal to negative 4x minus 10 plus 21. Okay. Oh, no, it isn't. My mistake, everybody. I am not thinking today. Get rid of this. There we go. I added 4x to both sides of the equation, not 21. Yeah. There we go. That looks a little bit better. So now this negative 4x will cancel off with this positive 4x. Okay. And then now on the left-hand side, 7x plus 4x is just 11x. And I still have this minus 21 is equal to negative 10, right? I'm going to add 21 to both sides now. Okay. So I have 11x minus 21 plus 21 is equal to a negative 10 plus 21. And so I'm going to get that this negative 21 cancels off with this positive 21. I have 11x is equal to positive 11. So x is just going to be equal to 1, right? So that's my solution there. X is equal to 1. Any questions on that? Any questions on that at all? Okay. Now we could check it if we want to, right? We could plug in x equals 1, and it does tell us to check it. So let's do it, okay? Hold on, let me pause and make sure that everybody's written this down, and then we'll check it. All right. So let's check it over here, I guess. So let's check. So here's my equation. X minus 3 over 4 equals 5 over 14 minus x plus 5 over 7. If I were to plug in x equals 1 into that, I get 1 minus 3 over 4 is equal to 5 over 14 minus, well, 1 plus 5 over 7. Okay. So over here, I get 1 minus 3 is negative 2 over 4. Over here, I have 5 over 14, doesn't change, minus 1 plus 5 is 6 over 7. Now, negative 2 over 4 is obviously negative 1/2, right? And over here, we got to get a common denominator, right? So then I can rewrite this as 5 over 14 minus, well, 6/7 is the same thing as 12 over 14, right? I wanted my denominator to be 14, so I had to multiply it by 2, right? I can't just multiply the denominator by 2, though. That would change the value of the fraction. So whatever I do to the denominator, I have to do the same thing to the numerator. So I multiplied both of them by 2. Okay, fair enough. Okay, so 12 over 14, same thing as 6/7. Now, I have negative 1/2 on the left-hand side. On the right-hand side, I have a common denominator, so I can just subtract the numerators. And now I have negative 1/2 is equal to negative 7 over 14, right? I can simplify that, and I get negative 1/2 equals negative 1/2, which is true. Okay. All right. Any questions on that? Okay. So these are all tricks we're going to use just automatically throughout the semester, right? Yeah. Okay. So now that I have that, right, linear equations with fractions, let's make it a little bit harder. Yeah. So let's talk about rational equations, which I don't think this is even the right section to really talk about rational equations, but we'll see. Rational equations can get pretty messy, okay? So I'll say this. We'll definitely return to this topic, so this will be treated in more detail later, but for now, not a formal definition now, right? But for now, we will restrict ourselves to a special subset of rational equations. Oops. Rational equations where the numerators and denominators are broken up into linear factors. That just basically means that you can factor everything as a linear expression, right? And we know what a linear expression looks like. Constant times x plus another constant, right? So everything factors as a linear expression, basically, okay? So linear factors there. Okay, so let's look at an example about 1 over x is equal to 1/5, right? Plus 3 over 2x. Okay, that's an example. All right. So let's solve and check this. Solve and check. Okay. Let's do that. Okay. So we got to find a least common denominator again, right? Okay. But now we have these x's in the denominator, right? So we have to treat that as its own thing. Okay. So x is, of course, the same thing as x to the first power. There's no factoring to be done there, right? 5 is already a prime number, so it's 5 to the first power. Right? 2x is just 2 to the first power times x to the first power, right? So the factors that we have there are 2, 5, and x, okay? So then your least common denominator is going to be 2 to some power times 5 to some power times x to some power. And remember that the power that we use, the exponent that we will use, is the highest powered exponent, right? So here, the highest powered exponent on x is 1, so it's going to be a 1 there. The highest powered exponent here on 5 is also 1, so it's a 1 there. Highest powered exponent here on 2 is 1, so it's going to be a 1 there. So then the least common denominator is going to be 10x, okay? Any questions on that so far? Okay. And if you want to work ahead of me, that's also fine, right? I'll catch up to you. Yeah, I just want to make sure everybody's on the same page here, though. Yeah. So now the next step is to multiply both sides of the equation by the least common denominator, right? Yeah. So I'm going to rewrite my equation over here. 1 over x equals 1/5 plus 3 over 2x. And I'm going to multiply both sides of the equation by 10x. So I have 10x times 1 over x. I have 10x times 1/5 plus 3 over 2x. Okay. On the left-hand side here, I'm multiplying by x, but I'm also dividing by x, so they're going to cancel to 1, right? So I'm just going to be left with 10 over here, right? 10 times 1 is just 10, okay? On the right-hand side, I got to distribute. Don't forget to distribute, all right? So I have 10x times 1/5 plus 10x times 3 over 2x, okay? All right. So then on the left-hand side, I still have 10. On the right-hand side, well, 10 divided by 5 is 2. So I just have 2x left here. Okay. All right. Over here, my x's will cancel off. Right. 10 divided by 2 is 5. So I have 5 times 3, which is 15. Okay. Let me know if I'm doing this too fast or anything. Yeah. Need me to go back through anything. All right. Well, now that we have that, right? Well, let's get my x's on the left-hand side and my constants on the right-hand side, right? So I'll start off by subtracting 2x on both sides. So I have 10, and I'm going to subtract 2x. And over here I have 2x plus 15, and I'm going to subtract 2x. Get some cancellation on the right-hand side. Over here I just have negative 2x plus 10, and this is going to be equal to 15. Okay. Now I'm going to subtract 10 on both sides, right? So I have negative 2x plus 10, subtract 10. Okay. 15, subtract 10. And so I get that this will cancel with that. So I have a negative 2x is equal to 10. Okay. And then now I'm going to divide by 2 on both sides, right? Or negative 2. So I have negative 1/2 times negative 2x is equal to negative 1/2 times 10. The negative 1/2 will cancel off with the negative 2 to 1, right? And then we get x is equal to, well, 10 divided by 2 is 5, so we have negative 5 here. Oh, why did I get 10 over here? You guys trust me too much. I think that's the problem. Yeah. So let's go back and fix that. All right. 15 minus 10 is, of course, 5 and not 10, right? Okay. And then now I have negative 1/2 times 5, which is negative 5/2. Okay. There we go. Okay. I'm not trustworthy. Okay. So x equals negative 5/2. Okay. Now comes the fun part. Let's check our work. Okay. This turns out to be super important with rational equations. Yeah. Okay. In this example, it's not going to matter, but I'm going to show you an example where it does matter. Okay. But first, let's do this. So let's check. So I have a 1 over x. So I'm plugging in x is negative 5 halves. So I have 1 divided by negative 5 halves. That already doesn't look fun. Okay. Equals 1/5 plus 3 over 2 times x is negative 5 halves. All right. Everybody okay with that? All right. Now on the left-hand side, although that looks horrible, it can be simplified quite nicely. All right. If I have a fraction and then I do 1 divided by that fraction, right? Well, let's just call it the reciprocal, right? Fair enough. The reciprocal is just 1 divided by whatever, right? Yeah, so the reciprocal of like 2 would be 1/2, right? The reciprocal of 3 would be 1/3, right? The reciprocal of a fraction is you just replace the numerator with the denominator. That's it, right? So here I have 1 divided by negative 5 halves. That's just going to be negative 2/5. Okay, negative 2/5 there. So that's not too bad on the left-hand side there, right? Okay. On the right-hand side, we have a 1/5 here, right? Plus a 3 divided by, and here in the denominator, I'm multiplying by 2, but I'm also dividing by 2. So that's kind of nice, right? Yeah, that's going to cancel off to 1. So we have a negative 5 left over here. Okay, so that's not too bad, right? So here, negative 2/5 is equal to 1/5, right? If 3 divided by negative 5 is the same thing as negative 3/5, so I'm really subtracting 3/5 here. So I have negative 2/5 is equal to, common denominator, 1 minus 3. So negative 2/5 is equal to negative 2/5. Check. Okay, it worked. That's great. Any questions on that at all? Any questions on that? All right. So now let's try something a little bit harder. I'm going to give you guys this one. This isn't going to be an active engagement assignment. I want you guys to kind of think about it for a little bit, right? So hopefully, if you get stuck, I'll come around. But I have got to get me some water. Okay. So solve this one, right? But once you solve it, check your work, right? And make sure that it actually makes sense in the context of the problem, right? Okay. I will be right back. So now let's look at common denominators. So in this one, well, this one doesn't even have a denominator on it. But remember, if you ever have like a whole number or something that doesn't have a denominator in it, you could just divide it by 1 and it won't change the value, right? Yeah. So, all right. Now let's look at the factors here in the denominator. I have an x minus 3, which can't be factored at all. So this is just x minus 3 to the first power, right? Same thing here. It's the exact same one, right? And then, of course, 1 is just 1 to the first power, right? So pretty clearly, the least common denominator here will just be x minus 3 to the first power. Yeah. Okay, so that's what we have to do. All right, we have to multiply both sides of the equation by x minus 3. Okay. Now, when we do that, make sure you put your x minus 3 in parentheses. Yeah, because the entire quantity x minus 3 is getting multiplied on both sides. Okay. So on the left-hand side here, well, let me rewrite the equation first. X over x minus 3 equals 3 over x minus 3 plus 9 over 1, right? All right. And I'm going to multiply by x minus 3 on both sides of the equation. I'm going to go ahead and distribute it to both the terms here. So 3 over x minus 3 plus x minus 3 times 9 over 1 is just 9. There we go. Okay, fair enough. Okay, so on the left-hand side here, x minus 3 divided by x minus 3 cancels to 1. So I just have x. On the right-hand side here, x minus 3 cancels off with x minus 3, so that cancels to 1. And I'm just going to be left with 3. And then plus 9 times x minus 3, I have to distribute, right? So here I'm distributing from the right there. So I get 9x minus 27. Okay. All right. So now that I have that, right, now I can subtract 9x on both sides, and I can simplify this. Let's just start with that, actually. 3 minus 27 is negative 24. Okay, negative 24. Okay, now I'll subtract 9x on both sides. So I have an x here. I'm subtracting 9x. I have a 9x minus 24 here, and I'm subtracting 9x. So that's going to cancel with this. We get out of here at 10:45, right? Okay, so we'll definitely finish this section today. Okay, x minus 9x is negative 8x. Okay, and on the right-hand side, we have negative 24. And then now we divide, oh, well, let me show the steps there. Don't want to jump the gun here. We're just starting, okay? So I'm going to divide by negative 8 on both sides. So it's negative 1/8 times negative 8x is equal to negative 1/8 times negative 24, right? So negative 1/8 times negative 8 cancels to 1. So we just have x equals negative 24 times negative 1/8. We're going to get a positive 3. There we go. X is equal to 3. Okay. All right, so that's our solution. X is equal to 3, right? Now let's go back and check it, right? So when we check it, plug it into here, we're going to get 3 over 3 minus 3 is equal to 3 over 3 minus 3 plus 9. Okay. Now that's a problem, right? Fair enough, because we can't divide by 0, right? So this simplifies to just be 3 over 0 equals 3 over 0 plus 9, right? You can't divide by 0. Okay, fair enough. So that's a real problem. We can't plug in x equals 3, right? So x equals 3 is not an actual solution. Actual. All right, well, I was going to correct it. Actual solution. Oh, we get this. All right. Hold on. This thing is very slow to respond here. Is not an actual solution to the original question. The original problem, I'll say. Right? We were trying to solve this equation over here, and we got x equals 3, which doesn't work, right? So let's think about that for a second. Because we did arithmetic, right? And we got this simpler equation, which should be equivalent to the equation we started with, right? And what does it mean for it to be equivalent? It means it has the same solution set. Well, clearly this equation has the solution set x equals 3. I could plug it in. 3 is equal to 3 plus 27 minus 27. So 3 is equal to 3, right? Yeah, it works for this equation. Why didn't it work for the original one if they're equivalent? And so the reason it didn't work is because we're dividing by a function of x. Yeah, fair enough. Yeah, so we can do arithmetic. We can multiply by any number we want to. We can divide by any number we want to except for 0, right? We can subtract any number we want to. We can add any number we want to both sides of the equation, and we always get an equivalent equation, right? But when we start multiplying and dividing by functions of x, then it might lead to something called extraneous solutions, okay? So we say x equals 3 is an extraneous solution. Extraneous solution. Cross that out. Extraneous solution, since it solves the simplified problem, but not the original problem. Okay, so that's what it means to be extraneous. And that can happen anytime that we're multiplying or dividing by a function of x. Okay, fair enough. All right. So now that we have that, right? Well, then what is the solution set for this for the original problem? Then the original problem has no solutions. Okay. Okay, and so on MyLab Math, some problems will be phrased this way, like you'll either like choose option A, which says the problem has no solutions, right? Or you'll choose option B, where you have to type in the different solutions, like you'll say 3, 5, 7. These are the solutions to the problem, basically, right? Yeah, on your MyLab Math, right? Or, right, sometimes, and this might not be in this particular textbook, but I know in some algebra textbooks it is, the solution set is written this way. Right? Have curly braces, right? You always put your solutions inside the curly braces, but we're just going to leave it empty this time. Okay? Yeah, because the solution set is empty. There are no solutions to this problem. Okay? Or here's another notation for that. Yeah. This is called the empty set. Yeah. It's like a circle with a slash through it. And it really is a diagonal slash. Let me see if I can do that a little bit better. There we go. Yeah. So that's another notation for the empty set. Exactly the same thing as that. So I've never seen it going the other way. I can't say for sure that it's not some other mathematical symbol. Yeah. But yeah, like in all the textbooks anyway, it's definitely going from the upper right to the bottom left. Yeah. Okay. Okay. All right. So good. So that's why we had to check our solutions in the case of fractional equations like this. Okay. Yeah. Super important. Let's see. 1032. Yeah. I think we'll definitely finish this section. Let's do one more of these types of problems, and then we'll talk about some special types of equations. Okay. So sometimes you'll see rational equations written the following way. Find all values of x for which y1 is equal to y2, right? And so y1 will be equal to, let's say, 1 over x plus 4 plus 1 over x minus 4. Y2 will be 22 over x squared minus 16, right? So it'll give you a y1, it'll give you a y2, right? Okay. All right, so now, when we're trying to find all the values for which y1 is equal to y2, that just means we're trying to solve the equation where the left-hand side's y1 and the right-hand side's y2, right? So let's show our work over here. We're really just trying to solve 1 over x plus 4 plus 1 over x minus 4 is equal to 22 over x squared minus 16, right? That's what we're trying to do, right? Okay, just as a little note to ourselves, or the problem's actually asking for there. Okay. All right, so we're gonna have to find the least common denominator, right? So let's see. X squared minus 16. Fortunately, that factors very nicely. This is called the difference of squares. Okay, so difference of squares, right? Why is it called the difference of squares? Because you have like an a squared minus a b squared, right? Where a is some quantity, b is some quantity. Yeah. Okay, so here x is being squared, and here 16 is just 4 squared. Right, so it's a difference of squares. Okay. All right, well, a squared minus b squared always factors as a minus b times a plus b. Right? When we can check it, right? We get a times a is a squared. We get a times b is plus ab. We get minus b times a is minus ab. So your ab cancels off with your minus ab. And then we get minus b times b is minus b squared. So we get a squared minus b squared. So when you FOIL it out, you see you do get this. Okay. Fair enough. So here your a is just x, your b is 4. So this is going to factor as a minus b times a plus b, right? Any questions on that? And we'll discuss the difference of squares formula later on also, and the difference of cubes formula. So, all right, so then your least common denominator, right, is of course going to be x minus 4 times x plus 4. Okay, yeah. Because if you look at all of your factors and the denominators, right, you have an x plus 4 to the first power, an x minus 4 to the first power, and this right here is just x minus 4 times x plus 4, right, all to the first power. So then that's your least common denominator, right? Okay. Any questions on that, by the way? Okay, good. I hope I'm not going too fast. I know I'm trying to finish the section up, but really, if you have any questions, just ask me. Okay. All right, so now I'm going to rewrite the problem here where I'm going to be multiplying the left-hand side and the right-hand side by this. So I have x minus 4 times x plus 4. And it has to be multiplied by the left-hand side here, which is 1 over x plus 4 plus 1 over x minus 4. Okay. And on the right-hand side here, it's x minus 4 times x plus 4 times, and I'm going to rewrite this as 22 over, I'm going to factor x squared minus 16 as x minus 4 times x plus 4. Okay. There we go. So I think you can see the right-hand side is really nice. I have x minus 4 cancels with x minus 4, x plus 4 cancels with x plus 4. They cancel at 1. So the right-hand side is, of course, just going to be equal to 22, right? 22 over there. Okay. Left-hand side, we had to distribute this, right? So this x minus 4 times x plus 4, that whole quantity is getting multiplied by the first fraction, but also it's getting multiplied by the second fraction, right? So I'm going to write this as x minus 4 times x plus 4 times 1 over x plus 4 plus x minus 4 times x plus 4 times 1 over x minus 4, right? All right. Now, cancellation ensues. X plus 4 cancels off with x plus 4 here. X minus 4 cancels off with x minus 4 here, right? Okay. So then I just have 1 times x minus 4 is x minus 4. Over here I have 1 times x plus 4, so it's x plus 4. I'll put it in parentheses, although I don't really need to, right? Just so you can see what came from where. Okay. Now I combine like terms. Minus 4 and plus 4 will cancel. So I have 2x is equal to 22. Multiply by 1/2 on both sides. So I get that x is equal to 11. Okay. So my solution is x is equal to 11. Okay. Any questions so far before we check it? Any questions? All right, well, let's check it then. All right, so we got to plug it back into the equation, right? So our equation was 1 over x plus 4 plus 1 over x minus 4 is equal to 22. So when we check it, right, we're going to plug in x is 11. So we have 1 over 11 plus 4 plus 1 over 11 minus 4 is equal to 22 over 11 plus 4 times 11 minus 4, right? Or 11 minus 4 times 11 plus 4, however you want to say it. Okay. All right, so let's simplify it a little bit. We have 1 over 15 plus 1 over 7 is equal to 22 over, well, this is just a 15 times a 7, right? Okay. So it seems like we're going to need to multiply both sides of the equation by 15 and by 7 in order to clear the denominators, right? Your least common denominator is 15 to the first power times 7 to the first power, right? Okay. Or you could plug it into a calculator. I'm going to show you something really nice. I don't know if I showed you this last class or not, but your calculator will actually tell you reduced fractions in most cases with small numbers. So for example, here I have 1 divided by 15. Oh, maybe I should turn it on. 1 divided by 15 plus 1 divided by 7 on the left-hand side. Okay. Now, if I just press enter, it's going to give me this decimal approximation, right? Yeah, which is not what we want, right? We want an exact answer. So I'm going to click on math. And this very first option over here is has this little triangle symbol and frac. That's the convert to fraction button. So I click on that. And then the answer, the last answer that I had over here, will be converted to a fraction. It's 22 over 105, right? All of the common factors have been canceled and everything like that. So over here, this is just going to be a 22 over 105. Okay, that's the left-hand side. On the right-hand side, well, 15 times 7 is 105. So it's just 22 over 105 there. Okay. So, check. Fair enough. Any questions on that? Any questions at all? All right, one last quick thing then. One last quick thing. And this is just on types of equations, just special types of equations here. All right, of course, we've seen linear equations and now some very simple rational equations anyway, right? But these types of equations go beyond that. So it's a definition here. So definition and identity. What am I writing on? There we go. An identity is an equation that is true for all x values that can be plugged in. Right. Fair enough. A conditional equation, on the other hand, a conditional equation, which is kind of that we're usually dealing with. In fact, everything in this section has been a conditional equation, is true for particular x values. Okay. An inconsistent equation. Inconsistent equation is never true. Right? There are no x's that satisfy that equation. Okay, fair enough. So we've already seen examples of these. I'll just kind of point them out to you, right? Oh, we haven't seen an example of an identity. So let's do an identity first. So example, identity. Okay, here's a really easy one. X plus 4 is equal to 2x plus 8 divided by 2. All right. Yeah, this is true for every single x value, right? If you simplify the right-hand side, you'll see that you get x plus 4, basically, right? Okay. Here's another example. X plus 2 is equal to, how about, do I want to do that? No, let's not do that one. Okay. Let's do this. So this is an identity. Now this, x plus 2 is equal to 6, right? Let's say this is a conditional equation, because this is only true for x equals 4, right? That's the only solution to that equation, right? So the left-hand side will only be equal to the right-hand side when x is equal to 4, okay? Now, an inconsistent equation, right? X plus 2 is equal to x plus 3. right? So if I combine like terms here, right? If I combine like terms here, I subtract x on both sides, I'm going to get 0. Subtract 2 on both sides, I get 1, right? I get 0 is equal to 1. Your x's cancel off, right? And then you have 0 is equal to 1. That is never true. Okay. Oh, what is this? Okay, there we go. So it's never true. All right, so just wanted to point out some examples of that before you start your homework on section 1.2 there. We'll go on to section 1.3, which will be really short, and then we'll go on to section 1.4 on Thursday, okay? So that order. Goes here. So let's stick it. There it goes. Yeah, sure. Okay.
So for this, is there like I can't cancel actions?
No, you cannot. So the only time you can cancel something out with the numerator, with something in the denominator, is when you factor it first.
Okay.
You have to. You can only cancel off entire factors. Yeah. Okay. Yeah. All right. All right. Have a good one. Rational equation. So this comes after that. You too. See ya. All right. There we go.